thankful for this opportunity to talk to you today about this project with Andy Lucas, who just spoke, and Ben McDonough, grad student at CU Boulder, and Chaoyuan, who is now a postdoc at Stanford. And it's about there's some relation to stability of phases and quantum simulation, or classical simulation of quantum dynamics. So there's some ties to the theme of the conference here. And so I'll first remind you about some aspects of Lieb-Robinson bounds and how they've been used in various aspects of condensed matter and quantum information theory, and where our result lies in that context. And then I'll tell you about two main applications, one to more traditional condensed matter physics, and one to bounds on classical resources for the simulation of quantum dynamics with error epsilon at time t. And then I'll give you a brief kind of flavor of the proof of these bounds and some directions for future work. So for the majority of the talk, I'll assume that the time evolution is described by time evolution with a finite range Hamiltonian, that's time independent. But you can also generalize to the time-dependent case, and at the very end, I'll tell you about how one can generalize to the case where the Hamiltonian itself has tails of a certain kind. Okay, so as many of you know, when you have dynamics generated by a local Hamiltonian, operators grow along within a light cone. And so this vertical direction is time, and we're evolving this local operator OI with a local Hamiltonian, and the majority of it lies within this light cone. And you can quantify that. So if you take the commutator of this time-evolved operator with another local operator OJ somewhere else in the system, then that commutator is very, very small. So if this operator is outside of the light cone. So if this I minus j is bigger than VT, then this commutator is really small. And so for simplicity, I'll take the case where these operators have norm 1, but we can generalize to other cases. And of course, if you just had like a finite depth quantum circuit, then there's no leakage outside of the light cone. It's just a tight light cone. However, if you have local dynamics generated by local Hamiltonian, then there's some leakage outside of the light cone. And the Robinson bounds is all about how do we bound that leakage outside of the light cone. There's many applications to how tight we can make the bounds on the leakage outside of the light cone. They can be used, as I'll discuss in more detail later, to bound the resources necessary for simulating quantum dynamics. They have been used in many, many different ways to study gapped phases of equilibrium quantum matter. So gapped Hamiltonians, for example, the stability of topological order. It was used in Matt Hastings' proof of the area law in 1D. It's used to prove the quantization of Hall conductance and many other things. And there's also other applications to quantum dynamics. And these are nicely reviewed in this review paper by Andy and Anthony Chan and Chaoyuan in 2023. So as I mentioned earlier, this operator grows within a light cone, and its leakage outside of the light cone is described by Lieb-Robinson bounds. And so to give some more qualitative intuition for what's happening, we can always expand the time-evolved operator OI of t in terms of polystrings. So any operator can be written in terms of polystrings. Let's just consider a system of qubits. And a polystring is just a tensor product of poly operators on different sites. So any operator can be written as a sum over polystrings. So can this time-evolved operator. So of course, at small times, the only polystrings with kind of non-negligible coefficient here will be within this light cone. But there's some leakage outside of the light cone. And so for example, you can consider the coefficient of the polystring that lies in this big region A. And using Lieb-Robinson bounds, we know that this coefficient has to be really small because it has to contribute very small amount to this time-evolved operator at time t. So by Lieb-Robinson bounds, the coefficient is bounded by this linear distance, this linear size of this region A. Now, the kind of unusual thing is that there are many other operators that you can write down that have much smaller support, but are bounded by the same Lieb-Robinson bound. So this operator here, if it appears in this expansion of this time-evolved operator, will also be bounded in the same way using the traditional Lieb-Robinson bounds. And so then the question is, do these operators actually have the same amplitude in the expansion of the time-evolved OI of t? So kind of what is the operator size distribution outside of the light cone? Our kind of intuition would say that this large operator is suppressed much more than this string-like noodle operator. But the traditional Lieb-Robinson bounds wouldn't be able to tell you that because it always gives you a suppression with linear distance. And so when we want suppression with something more than linear distance, we need to go a bit further. So to state again, Lieb-Robinson bounds give a decay in linear distance, and this is usually sufficient for everything we want to do in 1D and everything we want to prove in 1D. But when we want to prove things in higher dimensions, then we might need to go beyond this. And so one of the kind of technical tools that we will use is to, instead of bounding the single commutator, you can bound nested commutators, which tells you about whether an operator is simultaneously supported in many different places. And as we'll show, under certain assumptions, we can give exponential in volume tails rather than exponential in linear system size. So for example, then you can show that this contribution from this very large operator here, which is, will actually go as the volume of this region A. And so, as I mentioned, this kind of nested commutator tells you whether an operator is supported simultaneously on J1 and J2 and all these other sites. And this is the guy that we want to bound. And the rough picture is that we can actually bound this guy as a kind of, we take each of these points, J1, J2, J3, etc. And what you can do is you can draw a ball around these points, as long as these balls are separated by some distance greater than the range of the Hamiltonian terms. And then if you have a volume A, you can always fit in, like, order the volume number of such balls into this region. And you can make each of these balls such that the radius of the ball is bigger than Vt. So then you have order area, or order volume number of terms, and each of these can be made smaller than 1. You multiply all those together, you get something that decays with the volumes. And that's kind of, on the other hand, for this kind of noodle-shaped operator, you can't fit in so many balls. So this won't be governed by that same suppression. It's actually just suppressed by the linear size. Okay, so this is kind of the theorem that you get. If you take this big nested commutator, then you can show that this is, roughly speaking, bounded by the product of the Lieb-Robinson bounds between this volume V into each of these balls. And so you can choose these balls appropriately, and these sites, JK, and these balls appropriately, such that you can bound this by kind of the volume of this region, if this Vt is finite. Okay. So there are a few applications, and I'll mention 2 applications today. One is to properties of gap phases. And the idea is, let's suppose that we start off with a state that is close to the ferromagnetic fixed point. So what the state is, it's kind of a local unitary evolution away from the ferromagnetic fixed point. And this local evolution is Z2 symmetric. So we have kind of an Ising spin system, and we look at states close to the Ising ferromagnet. And of course, if you want to detect what phase your system is in, you'll try to compute order parameters, and you can also try to compute disorder parameter. So what the disorder parameter is it's the expectation value of this global symmetry operator truncated to a patch. So in the symmetric phase, then you would expect that this one to be more long-ranged. And in the symmetry breaking phase, you would expect this to decay very quickly. One issue is that, as I mentioned, the Lieb-Robinson bounds, these linear commutators will only give you a decay in the linear size of this region A, so you restrict the Z2 symmetry operator to a patch of linear size A. And that turns out to be not strong enough for some things that one might want to prove. And in particular, this actually goes against our intuition. The reason is, let's just pull this unitary evolution on the state onto Heisenberg evolution onto this operator. And if this unitary evolution is Z2 symmetric, then it only modifies this disorder operator near the boundary of A. So what this guy turns into is an overlap between two wave functions. And in one of them, you've basically flipped all the spins in this area, except there's some dressing near the boundary of this region A. So you'd expect this to actually decay as the entire volume of A, because you flipped all these spins, and the overlap is very small in the volume of A. And that is kind of in tension with this weaker bound given by Lieb-Robinson bounds. So you can show that using these kinds of nested Lieb-Robinson bounds, you can actually prove this stronger decay. And there are certain kind of very simple models where it looks like it's in the ferromagnetic phase. It has a long-range order parameter. It has area law entanglement entropy, but it actually violates this kind of stronger decay condition on the disorder parameter. And so you can use that to say it's actually not at least in the vicinity of the ferromagnetic fixed point. Another kind of application more related to quantum information and quantum simulation is for the classical resources if you want to try to simulate quantum dynamics on a classical computer. So suppose that we wanted to compute correlation functions of local operators under time evolution on a classical computer. Then the naive thing to do would be to evolve this kind of local operator OI with the full Hamiltonian. But you don't need to do that, because we know that we can truncate this Hamiltonian to this region A and evolve this local operator with the truncated Hamiltonian. And if we choose this region A to be large enough, then the kind of error between your full time-evolved operator and your time-evolved operator under the truncated Hamiltonian is very small. So what you can show is that you can actually take this radius of this region A to be t plus log 1 over epsilon, and that will give you kind of error epsilon in this kind of estimation of this local correlation function. And so what you can show is that for sufficiently kind of simple states, if this rho is simple enough, then the classical resource is necessary to compute these expectation values at time t will grow exponentially in t plus log 1 over epsilon to the d. And so what you can do is you can come up with a somewhat smarter algorithm and use these tighter Lieb-Robinson bounds to show that this is actually not tight. And there's a smarter algorithm you can do to actually bound the classical resources by, there's still a t to the d here, but now this is just log 1 over epsilon. There's no log 1 over epsilon to the d. And the kind of algorithm uses both a cluster expansion and a nested commutator bound. There was also a bound by this other paper in 2023, but their scaling with t was much worse, so it was e to the t instead of t to the d. But they still had the log 1 over epsilon. But ours is kind of better because we also assume certain spatial locality properties of the Hamiltonian. So how do you kind of do this smarter simulation? What you do is you basically take this OI of t and you expand it into how it leaks into each of these boxes. So you kind of tile the space with these boxes of linear size vt, roughly vt, and you can expand this operator OI into its contributions from how it leaks into each of these boxes. So I've drawn one such S here. And then you can use bounds on the number of connected clusters to bound the number of such configurations of boxes. And then you can use the nested Lieb-Robinson bounds to bound how much error dropping out large clusters gives you. And combining those two things, you can show that now if you truncate this sum to the clusters that are smaller than a certain size, then the error is actually quite small between your approximation of the operator and the original fully time-evolved operator. And so what you can show is that there's a choice of these box size and the number of boxes such that this, putting all these resource counts together, you get kind of the bound that I gave you on the previous slide. And we believe that this is tight. So this is basically as good as you can get in terms of like what kind of classical resources you need for generic quantum dynamics. Yeah?
An exact simulation of, like, if I had, like, attempted to do something like this with dense networks, what kind of time would that take?
So I'm not sure what you mean by if I try to do this with tensor networks.
I used a different, like, approximation scheme.
Oh, yeah. Like other algorithms would give you other kinds of error, right? So I don't know if this is just like, oh, if you did this algorithm, then this is like very, very as tight as you can get, probably, and then you will get very small error even with minimal resources. But if you use some other algorithm to try to simulate these kind of correlation functions, you might not be able to get as tight.
Okay, maybe I didn't understand your claim. So when you said that this bound is tight, did you mean that any classical algorithm which simulates this dynamics with this error will have a resource cost something like this, or did you just mean that this algorithm has resource costs something like this?
Well, what I mean by tight is there's kind of a simple example that you can try to cook up that kind of saturates this bound. So it really does require that number, that runtime in order to get this small error.
Using this algorithm or using any algorithm?
Using any algorithm. And the reason is because you can, there's like a simple example where like in 1D, basically the Lieb-Robinson bound on the kind of resources is tight. And then there's kind of a higher dimensional example you can build off of the 1D example to show that you probably actually do need that amount of runtime to estimate up to that error. But yeah, I can. Okay. Cool. Yeah, in 1D, there's like just dynamics you can show pretty much saturates the resource bounds in 1D. So, okay, so those are kind of the statement of the results and some applications. The proof of the result is a bit technical, but I wanted to just give you some flavor of the techniques that one would use. So to prove let's first start with proving the single commutator, the original Lieb-Robinson bounds, before getting to these nested commutators. So for the original Lieb-Robinson bounds, the most naive thing that one would do if you want to bound the commutator between a time-evolved operator and another operator far away is to just expand this time-evolved operator using kind of a BCH expansion. And so you just take the commutator of OI with H, and then the double commutator, et cetera, et cetera, et cetera. And now let's put these points on some lattice. So I is here, J is here. Maybe the lattice is much larger than this, and I've just drawn some small portion of it. And the Hamiltonian, let's, for simplicity, just consider a Hamiltonian with two body terms. So then this first commutator of OI with H will pick up all the terms in H which overlap with I. All the other terms in H will just commute through OI, so they kind of die. And then the second commutator will give you kind of terms that look like this, where you've captured two Hamiltonian terms in this nested commutator. And as you continue, what you find is that the first term in this expansion, this BCH expansion, like contributes non-trivially to this commutator is a string of Hamiltonian terms that take you from site I to site J, because now that will have a non-zero commutator with OJ. And this string has some very small weight. So it has weight like 2t to the I minus j over I minus j factorial h, which is the kind of norm of a single Hamiltonian term to the I minus j. So this is even faster than exponentially small in I minus j. The problem with this kind of approach is that there are many other terms that contribute to this commutator. So now if you go to the next order, like take another commutator with a Hamiltonian, this term will contribute, and these terms will contribute, and you'll end up finding that you're summing over all of the trees that kind of intersect with I and J, and that will not converge in general dimensions. And you kind of expect it to not converge, because you, in this kind of formulation of the problem, you've lost track of the I in this e to the IHT. And so you could have done the same thing with imaginary time evolution, and there's no Lieb-Robinson bound for imaginary time evolution. And so you need really to use a method that uses this I, and you need to use a method that takes advantage of the fact that unitary, like conjugation by unitary, doesn't change the operator norm. So then what you can do is, in this method kind of nicely summarized in Hastings' review paper in 2010, there's a lot of smart pushing operators and unitaries through the operator norm. And if you do that, and if you push unitaries through the operator norm, what you can do is you can get rid of all of these, most of these trees. And so you end up summing over the paths connecting I to J, with some small repeats and some small branching off of the path. So the name of the game here in terms of bounding, doing Lieb-Robinson bounds, is just to try to get rid of as many of these kinds of contributions as you can. And this is actually good enough to give you the traditional kind of Lieb-Robinson bounds. But you can actually do slightly better. So in Chen and Lucas in 2021, they show that you can actually get rid of more contributions to the sum. And in particular, this guy and this guy can lie in the same equivalence class, because you can remove those two terms and you still connect I and J. So they have this equivalence class formulation of counting paths to bound Lieb-Robinson bounds. And then this actually gives you the tightest possible bound, because now you're summing over the fewest number of contributions to this commutator. Basically, this path and this path, they don't independently contribute. You can kind of just add this contribution once to your sum. And then in 1D, this actually gives the tightest possible Lieb-Robinson bound. So this is, you find that this naive first contribution from the expansion is actually the only thing that contributes. And this is even faster than exponential. It's like e to the minus r log r, r over log r. Yeah, r log r, sorry. Okay, so in the single commutator case, we had this one BCH that didn't really work at all. This other method by Hastings and other people that works but is not completely tight, and this equivalence class method that probably gives you the tightest bound. And now we can look at how these function for nested commutators. So now let's consider the simplest possible case where I have two operators, OJ1 and OJ2. And again, the first term that contributes to this kind of BCH expansion is of order, is like exponentially small in this area, because you need a nested commutator such that it touches all of these guys in order to give a non-zero contribution. But as in the case before, there are many, many other contributions to this nested commutator. So you have all of these trees, and if you try to count all those guys, you won't be able to get something that converges. Now, if you try to use the kind of Hastings type approach, then you might get something that converges, but it's very, very hard to compute. And the reason is, now what you find is you're counting kind of paths, two branched paths that start at I and end at J1 and J2. However, there are many such two branched paths, this one and this one and this one. They all kind of contribute. And so in principle, maybe you can count them, but it's very difficult to do so. And so this is one case where this equivalence class method by Chen and Lucas was really able to shine and have a nice application, because it was really crucial for us to use this in order to get any sort of like nice bound. So what you do is you put all of the two branched paths that look the same outside of this region B1 and B2 into the same equivalence class. And so this is maybe that it will sacrifice some scalar factors. So this is not as tight as you can, but it will give us at least the right scaling with kind of T and area and those kind of things. And so you put all the two branch trees that have this look the same outside of this B1 and B2 regions into the same equivalence class, and you just count them once. And so if you do that, the idea is that basically this will just kind of become a Lieb-Robinson bound from this outer region into B1 and into B2 separately. And so you can do this for arbitrarily many number of nested commutators, and then that's how you get this result that I showed previously. And you can also, and so the basic physical intuition is that when you have an operator and you time evolve it, it leaks outside of the light cone. But what is the kind of operator size distribution outside the light cone? It turns out that it doesn't kind of leak outside of the light cone in balls. It leaks outside of the light cone in these thin noodles, because those are the ones that can stretch outside of the light cone and have the smallest suppression. You can also extend this result for finite range Hamiltonians to Hamiltonians that have tails. So that's what we call quasi-local Hamiltonians. And so you can consider a Hamiltonian that has spatial locality because you're summing over connected subsets. And these Hamiltonian terms are suppressed in the volume of that set. And you can prove kind of a similar Lieb-Robinson bound. It's a lot trickier because now you can't kind of decouple these different balls completely, but after a lot of algebra and work, you can work this out. And so these kinds of Hamiltonians are relevant because, especially because in recent work from last year, these papers show that in the vicinity of kind of fixed point states, there's kind of a quasi-adiabatic continuation generator that actually has this very nice locality property. And I can say more about that if there's interest. Okay, so that's kind of the brief summary, but there are it's very interesting to kind of think about if there are other applications of these sort of bounds on extended operators. So for example, one generalization, technical generalization would be what happens to H of T with other kinds of decay. Because we had some very specific kinds of decay that we considered. It seems like there might be some relevance if you are trying to prove of these kinds of bounds on extended operators to trying to prove the area law in higher dimensions. The reason is if you considered a 2D system and it's just kind of a stack of 1D systems and operators grow in 1D, then there's clearly an area law because you cut the system and then you just get a contribution from each 1D system. So any kind of obstruction to, or like difficulty in proving the area law in higher dimensions probably come from how operators grow not only in 1D, but kind of grow in a whole 2D or higher dimensional region. And those extended operators are kind of the focus of the bounds that I talked about today. There's also, because you can use these kinds of bounds, the assumption of this very strong, quickly decaying quasi-adiabatic generator to prove certain things about scaling of order, disorder parameters, et cetera, in gap phases, this kind of also gives kind of physical reason to try to search for such stronger quasi-adiabatic generators that work for the entire phase. The ones that I showed by the two papers on the previous slide, they can only be guaranteed for some order 1 patch or region around fixed points. And of course, yeah, because Lieb-Robinson bounds have found so many applications in properties of gap phases and dynamics, one can ask if there are other applications that I didn't talk about today where you can make use of these bounds on extended operators. Okay, thank you for your attention.
Thank you, Carolyn, for a very nice talk. Any questions?
So just wanted to make sure this bound holds for the extended operator too. Like in 2D, let's say you have like an operator supported on some like a radius r annulus, and if you apply this thing, you still get something that decays with like r times the like say so you evolve for a time t, then you get the decay that's like exponentially small in r times. Well, I guess basically my question is, do you get like exponentially small in R dependence or not in this setup?
So is your initial operator, so this is the statement about if you take some local operator and you time evolve it, what portion of the operator becomes supported in this extended region? So do you want to take a local operator and evolve it and ask what portion of this operator is supported in this annulus? Is that the question?
No, like it's like a general operator on an annulus. Then do you get the bound that decays with R or not?
So you want to start off with an operator supported, you want to start off with an extended operator.
Like a string operator, yeah.
A string operator. Yeah, so then, yeah, so strictly speaking, we looked at the evolution of point-like operators. But of course, if it's unitary evolution, I guess you can just compose all those evolutions on all these different points. And then you can show that, I guess, around each of these operators outside of their Lieb-Robinson cone will grow like a noodle outside of that. So that would be the contribution to the growth of the string-like operator as well. I would assume that outside of this annulus, it kind of leaks out in these noodles as well.
Okay, thanks.
Do you have a page with all the qualifiers? What R is?
With all the what? Sorry?
I mean, the statement involved symbols like a capital R, which does not appear anywhere else. So I forgot what a capital R meant.
Oh, so this is this R is like this R here, like the linear size of the region. Because what we're trying to say is that this time-evolved operator, if you look at the portion, like its support on all these kind of points simultaneously, how much is that suppressed? And instead of linear in this linear size of this region, then it's the volume of that. Okay. So the idea is that you take all of these kinds of points of interest, J1, J2, J3, etc., and this is your original local operator that you're time evolving, and you can draw balls around these points as long as they're separated by the range of the Hamiltonian. So you can make those balls as large as possible to get the largest like the tightest bound. And then, then you can bound this kind of nested commutator with the individual Lieb-Robinson bounds from the complement of this region into each of these points. So how this operator, like this complement of the region, leaks into the center of each of these points.
Thanks for the interpretation, but I asked for the statement page.
Okay, so I guess one statement is, like if you work a bit harder than this, then one statement you can make is, suppose that I decompose my operator OI of t into a sum over Ci of t sigma nu, as I mentioned earlier. Can you see this?
No.
Oh.
I guess you can just go to the bound page where the.
But maybe this is a better way to state it. So I take my operator OI of t, and I write it as a sum over all the polystrings with appropriate weights. Okay. And now let's take like all of the size. So I take all of these kind of polystrings such that the support is greater than some size s.
In weight or?
In weight, yeah.
Okay.
Yeah. So this is like the contribution to this big operator expansion from operators that have support greater than some size s.
Okay.
And so this is, you can bound as This is kind of the thing that we're trying to show, essentially. If t is finite. If t is not finite, then there's some modification.
Oh, thank you.
Maybe a technical question, like, do you expect this to be generalizable if all the operators are at different times?
Yeah, so that's a bit of a different question because this is asking if the OI of t evolves in time contributes to operators that are supported. And so at this point, this J1, J2, J3, et cetera, are just kind of probes for operator support of OI. So I guess now you're asking, you also want to evolve like J1 or J2.
Right, if there are dynamics, like if they add as like perturbation at some time, and then you want to see how they propagate, and do they have correlations? I don't know if that's a...
Yeah, so if you just have two, then that would be of a flavor of an OTOC, I guess. And in that case, you can study OTOCs using Frobenius norms, which is kind of beyond what we did in this paper. And then I'm not sure about, if you added time dependence to other.
Okay, thanks.
Any other questions? I guess if not, let's thank Carolyn again. So now we have a coffee break until 11 when we will resume the second part of the morning session.